There we go. And then, anyway, okay. So as I was saying, so we spent all the semester discussing all the combinatorial background for this statement, right? But we never discussed how to prove it. And it turns out the proof is actually quite complicated and involves a lot of different pieces, which is why we needed all this background to understand also, I mean, the motivation of the statement, but also how it's actually proven. And we'll still have to introduce a couple of other things, not so much today, but in the next talk. So without any further ado, let me just get right into it. So like I said, today, we're mostly gonna just review some combinatorial stuff and basically translate the statement of the shuffle conjecture that we saw last time to what actually got proven in the paper. And we'll see why those things are equivalent, why it is actually a proof of the shuffle conjecture. Okay, so just to do some combinatorial preliminaries, right? So we're gonna let D be the set of dict paths. Right, and this is of any length. These are square dict paths, so n by n squares. And we're going to use the notation ij. We're going to call this a cell. So a cell labeled by ij. If in your dict path, we're talking about this cell where this is coordinate ij. So it's this cell that we're referring to, right? So ij is the northeast corner of the box of the cell. So this notation will come up a lot. So just as a reminder, right? So the area of a dict path is just going to be the number of cells. Hopefully remember this, that lie below the dict path, but above the diagonal, right? Where I and j is a cell under pi in D. This is too fat. And then the area of pi is just going to be the cardinality of this set. It's the cardinality of area of pi. And then associated to this, we're going to construct a sequence. We're going to call it AJ, which is basically the number of cells in the area for any given column. Sorry, for even any given row. So here we're in row J. Okay. And so from here, we can construct what's known as the area sequence, which is going to be denoted by A of pi. And it's really just going to be A1, A2. It's just, you know, exactly as you would expect, AN. Where obviously the area is then just going to be the sum. So the area of pi is just going to be the sum of the AIs, right? Okay. And then associated to this, we also have something that's known as the co-area sequence. So co-area sequence. And what that is going to be is, so we're going to denote it x of pi. And what's going to be is, 1 second. It's going to be the sequence that's defined by the fact that x1, 1, x2, 2, etc., all the way to xn, n are cells in the same row and immediately to the left. Immediately to the right of each north step. So this is really easy to understand with an example. Right, so if we have some sort of dict path, let's say something like this, anyway, whatever, make it square. The area is just, well, you know what the area is because we've seen this before, but the co-area is just going to say, well, to every north step where this is a cell that lives in here. So this would be x1, 1. Here we take another north step, and here we take another north step. So this would be x2, 2. This would be x3, x3, 3, and so on. And so you basically, right, you'll notice that for every row, you pick up a new box, and which is why the second coordinates is just going to be 1 through n, because you have a total of n north steps, right, and so on. So it's just these boxes. So these boxes are the cells that make up the co-area sequence. Okay, and what that means is that if you sum up AJ plus XJ, you get precisely J, right? Okay, cool. So let's do an example. Or actually, well, let's continue, because I think this example, we know what area and coarea are. So then we also have these things called DINV, right? The diagonal inversions. So I'm going a little bit quickly through this just because there is a lot of material. And this is something that we did before in the semester. So do stop me if something is not clear, of course. So div of pi is then going to be the set of cells, we're going to call them JJ prime, where we have 1 is going to be less than or equal to j, less than or equal to j prime, less than or equal to n, such that the their coordinates in the area sequence are the same, unioned with the sequence j prime j, or the cells j prime j, such that 1 is less than or equal to j, less than or equal to j prime, less than or equal to n, and aj is equal to aj plus 1. And I forgot a prime. So again, and of course, little div of pi is just going to be the cardinality of big div of pi. So an example is if we do, let's say, 2 steps north, 2 steps east, 1 north, 1 east, 1, 2, and then 1, 2. Right, so this is our dig path. Then here, the area of pi is going to be what? It's going to be the sequence 0, right? Because we have 0 area in column in row 1. Then we have 1 box in row 2, so it's going to be 1, 0, 0, 1. I'm just counting the number of boxes per in the area per row. And then chi of pi is going to count the number of boxes in each row that are next to an up step, right? A north step. So here we're going to get 1, 1, 3, 4, 4. Because these are the coordinates of the x coordinates. Sorry, yeah, the x coordinates of each box. So to say that more clearly, right here we have this, but then here we have a north step. Here we have a north step, and here we have a north step. So these are the boxes that would correspond to the co-area sequences. These right here, right? And then you'll see that this has x coordinate 1, x coordinate 1, x coordinate 3, x coordinate 4, and x coordinate 4. And that's how I'm getting this sequence right here. And then what that means then, if we just look at the definition, is that then the div of pi would correspond to what? So we want to look at the sequence a pi and say, all right, we want coordinates, let's say 1, 2, 3, 4, 5. We want coordinates such that aj is repeated with aj prime. So 0 and 3, so you get 1, 3, you get 1, 4, right? And we get 3, 4. These are the repeated ones. And then we get 2, 5. Right? And then you want to look at sequences where j is 1 more than the one after it. So we look at 2, 3 and 2, 4, right? Because 1 is bigger than 0 and 1 is bigger than 4.
And you wrote j prime comma j.
Yeah, and that was exactly what I was going to say. Exactly. And then you'll notice that here it's not j comma j prime, it's j prime comma j. So you need to flip those entries. So okay. This is really 3 comma 2. Yeah, thanks, Monica. It's just easier to think of like writing them in the wrong order and then flipping them.
Yes, that's totally fine.
Yeah. And then you flip this one, 4, 2. Right, and then this is your actual sequence of div. And then of course, little div of pi is just going to be however many of these there are, which is 6 or 5. Did I get something wrong? No, wait, maybe I'm 3, 4. It doesn't match up with my example, which is why I'm concerned. Did I say something wrong? 1, 3, 1, 4, 3, 4, 2, 5. Oh, maybe I did something wrong in my handwritten example, probably, because this seems right. Okay, now we also learned about word parking functions. So what are these? So these are words in Zn bigger than 0, such that they're decreasing in each column, right? i.e., if you want to think about this in terms of our co-area and area sequences, it's just telling you that wj is bigger than wj plus 1, where these are the entries in your word, whenever xj is equal to xj plus 1. Okay, so if we just look at our example here, so let me just maybe empty the boxes. So if we look at our example, and let's say we looked at, well, do I want to do that? Yeah, that's fine. So this would be 4, 3, 8, 2, and 5. Let's suppose we looked at this particular word. Right, then in this case, the word parking function, so example from above, then our word would be 3, 4, you just read it up, 8, 2, 5. And you'll notice that it's decreasing, right? So that's the only condition. Okay, what else? And so this is a new statistic that we haven't seen before, or maybe we did, I don't remember. So we have this thing called the touch composition, and this will actually play a key role. So this is very much worth remembering. So the touch composition is going to be a composition alpha, let's say alpha 1 through alpha k. And it's going to be defined in a sense that alpha measures the touch point. So it measures the gaps between the diagonal touch points of pi, right? In the sense that you also get alpha I equals to n, obviously, right? Because it's just the diagonal point. So if we go back to our example, right, then here, the touch point, you're going to get a point here, and you're going to get a point here. So this is 2, this is 1, and this is 2 again, right? And so here, in the example from above, we'd get that alpha is 2, 1, 2. Okay, good. Are we good on the statistics? I went through them fairly quickly. I can do one more bigger example if anybody would like, so that we really understand these statistics, but if not, I will just move on. Okay, seems like we're good. So then, with all these statistics in hand, let's recall what the shuffle conjecture, as stated, tells us. So the shuffle conjecture says the following. It tells you that -1, and there's a -1 here that is a little bit different from what we saw in the book, if I remember correctly, but they're the same conjecture and they're equivalent, so don't worry too much about the -1. So is t to the area of pi, right? Where here we're summing over pi in n by n paths.
Nicole, quick question.
Yes.
For the touch composition, is the alpha going from bottom to top or from top to bottom?
From bottom to top, yes.
Okay.
So this is starting at, that's a very good point, starting at 0, 0.
All right, cool.
Yes.
Thank you.
Okay, so a shuffle, yeah, this is not a very, this is unfortunately too symmetric. Yeah, so the shuffle conjecture tells us what? That if we take -1 to the n of nabla en, this is the sum over dict paths, and by n dict paths, of t to the area times the sum of q to the dinv of pi w. Oh, I didn't tell you what pi w was. Let me remind you of that. Where this, you're summing over, or sorry, not that. You're summing over word parking functions of pi. So maybe let me, I realized I forgot to tell you what dinv of pi w was. Okay, so then one more statistic we need to remind ourselves of. So we have dinv of pi w, which is what? So it's the set of all cells, right? J prime in the set dinv pi. So you're keeping that same set such that Wj is bigger than Wj prime. And then I'll compare it to the example in a second. And then of course, little div of pi w is going to be the cardinality of this set. So this is pretty standard notation. So if we go back to the example above, right, where we had, let's say 2, and then 2, 1, 2, and then 2, right? And what was our function? It was 4, 3, 8, 5, and 2. So here we had that, just as a reminder, our word was 3, 4, 8, 2, 5. And then div of pi w is going to look at the cells in div of pi, which was here. Let me copy that over. So div of pi was here. And we're going to look at the cells here such that, well, this condition holds, right? So 1 and 3. So we're going to look at word 1, 2, 3, 4, 5. I'm just writing that for my own. It's much easier to see. Is 3 bigger than 2? Yes. So we get the cell.
Wait, you said 1, 3. So should we be looking at 3 and 8?
Oh yeah, thank you. Yes, absolutely.
Mhm.
Thank you. So 1 and 3. So 3 and 8. So 3 is not bigger than 8. So that doesn't work. 1 and 4. Is 3 bigger than 2? Yes. So we get the cell 1, 4. Does that everybody agree? Am I right?
Yep, that looks good.
1, 4. There's like a lot of numbers and I end up comparing the indices instead of the actual values. Sorry. So then we look at 3, 4. So 3 and 4. So is 8 bigger than 2? Yep. So we get the cell 3, 4. 2 and 5. So is 4 bigger than 5? No. 3, 2. So is 8 bigger than 4? Yep. So we get 3, 2. And 4 and 2 is 4. Is 2 bigger than 4? No. Okay, hopefully I did that correctly.
So, yeah.
It might be wrong. The definitions are
Doing
right.
the 4 and the 4 and
Might be
2
wrong.
got particularly tricky, but I think it's right.
Okay, great. And so then in this case, that means that little div is going to be 3, right? It's just the cardinality. Okay, so this is the shuffle conjecture as we saw, or very similar to what we saw before. Like I said, it's an equivalent formulation. Don't worry too much about the -1 hanging out in front. And what we actually want to prove, which is what they actually did in the paper, is they prove a modification, a refinement of this known as the compositional shuffle conjecture. So the compositional shuffle conjecture. So this was conjectured by Hagland, Morrison, Zabrocki. And what the refinement says is the following. So the refinement tells you that if you take -1 to the n of nabla of another operator called C alpha, tell you what that is in a second, of 1, that this can be written instead of summing over all of all dict paths, we're only going to sum over dict paths that are indexed by a very specific composition that determines its touch sequence, essentially. Right? So we're going to sum over dict paths whose touch sequence is equal to alpha. And then the rest of the sum is essentially the same. So this is area of pi. And this is, again, we're still summing over word parking functions. Q to the div of pi w xw, right? So where does this statement come from? I'm not going to tell you how they came up with the sequence or how they proved it, because that's a whole different paper, which I recommend you read this paper. It's fantastic. But essentially what they showed, so the idea behind this statement is that they showed that these operators, again, C alphas, whatever they are, I'll tell you about them. So these operators, C alphas, when you sum over compositions of size n, give you precisely En of X, right? So these are certain series, the C alpha is a certain series that are defined in terms of two parameters, X and Q. And somehow when you sum over all weak all compositions of size N, you recover the nth elementary symmetric function, which is a crazy identity. And then at this point, it's just a matter of applying nabla to both sides, right? Because then you get that precisely, you apply nabla C alpha here, you get exactly -1 to the n, nabla En, which is why the compositional shuffle conjecture is really a refinement of the shuffle conjecture. If you prove the compositional one, you get the shuffle conjecture by just summing over it by exactly this identity right here. And that's exactly what Carlsson and Mellit did. They focused on the compositional shuffle conjecture, not the original one. Okay, so what are the C alphas? We'll see that later. It's just some function. For right now, we don't have to worry about it. What we're going to worry about for the next however long it takes me is this side of the equation. So the first goal is we're going to reinterpret that sum to a different setting where instead of area and din, we're going to talk about inv and bounds. And the reason I'm going to go into detail is because the bijections that we saw in the seminar previously that are in Hagel's book are different from the bijections that they use in this proof. So even though you still get bounds in area, which we saw a construction for this previously, it's a different construction. And it's really interesting. It's really pretty. So I think it's worth going through and actually seeing how they constructed this. Okay, so that's what we're going to do now is ignore this part. We're not going to worry about that right now. We're just going to worry about the combinatorial side. So what is the first goal? So goal 1, or actually maybe before I say this. So let me just write it. So Carlsson and Mellit, right? What they did is they rephrased everything, basically. Everything, I don't know how to spell. From area and din to bounds and area. Right, and the way they did this is that they changed our pi w to some other dig path and some other word. So with that in mind, our first goal is to construct what this dig path w is, or pi prime, sorry. So construct pi prime, the new dig path. So what is the first thing we want to do? So step 1. So given pi, you want to read the cells x, j, comma, j across diagonals. So this seems like it's basically a recipe. So across the diagonals, bottom to top, and then left to right.
And so just to check, this is going to be like the sweep map or the zeta map.
In their paper?
This map that we're going pi to pi prime.
Yeah.
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 Yeah. Yeah. And I should point that map is due to other people. I mean, they used it, but it was.
Oh yeah. Okay, fine.
Like,
I know there is like the bijection they use from area to bounds, I think, is new.
Okay.
I'm not saying every piece of this is new. I'm just saying that this is not necessarily the same bijection that was in Hagel's book, which is why I'm going through it. That's yeah. Okay, great. So then you just read across the diagonals, right? So if you have, for example, pi was let's say 2, and then 2, 1, 1, 2, and then 1, or then 2. So what are our entries? So here we have 1, 1, we have 1, 2. So I'm just reading the boxes in this set, right? So this is 3, 3. These are the co-area sequences. This is box 4, 4, and this is box 4, 5. All right, so let me just make that really clear which boxes I'm talking about. Right, these. So the idea is you just read across the diagonal. That's one diagonal, and then this is the second diagonal. All right, so then we get the sequence 1, 1, 3, 3, 4, 4, 1, 2, and then 4, 5. Right? Okay. What is the second step? So step 2.
Wait,
That's
is that
it.
left to right or right to left? Wait. So you said
Bottom to top.
bottom to top and left to right.
So bottom to top across the diagonal. So you read the bottom diagonal first, which is bottom to top,
Yeah.
and
But
my
that-
left to my right.
The other diagonal is to the left of that, right?
Oh, I guess I was seeing like 1, 1 is to the left of 3, 3.
Oh, I was thinking about like your 1, 2, 4, 5 diagonal. So,
Yeah, and 1, 2 is to the left of 4, 5.
correct. Oh. Oh, I see. Okay. I figured that bottom to top took care of that.
Oh,
Like,
okay.
So I can see that, 1, 1 versus 3, 2, 4, 4.
Yeah, I
I
guess
see
the
that
whole
as
point
being
is-
bottom to top, but you meant the diagonals were bottom to top and then along with, okay.
Yes.
Got it.
So,
Okay.
I mean, ignore the bottom, top, left to right. Literally just look at the diagonals and read each diagonal, bottom to top, across the diagonal, if that makes any
Yeah.
sense.
Yeah. No, I just your left to right. I thought I'm
I
good.
understand the confusion.
I'm good.
Okay. And then step 2 is
Nicole?
to, yeah.
Could you write a tiny bit bigger for the things under the diagonal? It's getting a little hard to read.
So
Like
all
I know what it's supposed to be, but just for like future things.
Okay.
Just a warning.
Okay. Yeah, I was just trying to, it's just a labeling of
Yeah.
the entries.
Thank you. Sorry.
Absolutely. Here, I can even make this bigger. Is that better?
Yay. Thank you.
Okay, so then step 2 is to construct a permutation. Sigma. And how do we do that? So we're gonna let sigma j be the position of xj comma j in this list, right? So if we look at our example above, here's sigma. We'll just let 1, 2, 3, 4, 5, 6. Oh, this is the wrong example. So 1, 2, 3, 4, 5. And if we do that, well, we just basically, right, we say, all right, what did 1? 1 ended up in position 1. What about 2? 2 ended up in position 4. What about 3? 3 ended up in position 2. 4 ended up in position 3. And then 5 ended up in position 5. So I'm just reading this list, and I am reading the second coordinate. Right, so I'm just looking at these entries. Okay, so that gives us sigma. Excellent. And then third step, so step 3, is to define pi prime to be the unique dict path such that the area of pi prime is given by the sets sigma j prime, such that j comma j prime are in div of pi, right? Which you can think of this as basically just applying the permutation sigma to div of pi, right? So in our case, what is that going to look like? So did I do this example in full detail? I kept on working with 2 different examples, which I realized was a bad idea because I have pieces of both of them at different components, which is terrible. Okay, so let me just, it doesn't seem like I did it, but let's, oh no, I did. Oh, great, awesome. Okay, so then if we go to the previous example, so example, right here, the area of pi prime is going to be, well, we just do exactly what this is saying. Right, we see we're going to get the set 1, 2, y. Cool. Okay, so we're going to look at these pairs that were in div of pi. So where on earth is div of pi? Let's go find it. Div of pi w or just div of pi? Div of pi. Okay. So we're going to go back, copy this, copy. So we have div of pi. And then it's just a matter of basically translating everything through, right? So do check me. I'm at this point just copying what I had in my notes, but there's probably a mistake. So please do check me. I think I'm missing one. Because I should have the same number. So which one am I short? All right, so 1, 3 is 1, 2. 1, 4 is 1, 3. 3, 4 is 2, 5, which I apparently don't have. 3, 4 is 2, 5.
Wait, isn't 3, 4, 2, 3?
3, 4 is 2, 3. Yes, it is. Which I still don't have. 2, 3. 2, 5 is 4, 5, which is here. 3, 2 is 2, 4, which is here. And then 4, 2 is 3, 4, which is here. There we go. Okay, this is it. So I knew I was missing one. Great. So there you go. So this is area of pi prime. And so then looking at this, it's just a matter of drawing the sequence that you need to have, right? So let's just actually work it out. So, so this has to be a 5 by 5 box, right? So I think I have too many boxes. Yeah, I do. Sorry, guys. I thought I had the example. I just realized totally incorrectly written in my notes, which is because I missed a point in div previous in when I did it, which was a bad idea. Okay. So we need box 1, 2 to be in the area. So I'm just gonna write this in orange. So box 1, 2 is this one. And then we need box 1, 3, which, wait, it's backwards. So 1, 2 is this box, sorry, right? 1 and 2. 1, 3 is this box. Box 2, 3, so 2, 1, 2, 3 is this one. And then 2, 4 is this one, right? So I'm just drawing these. Then we have box 3, 4, so 3, 4 is this one. And then we have box 4, 5, which is this one. Right, and so then our dict path is uniquely defined as basically just follow exactly what this is. There's your dict path pi prime. Is that clear? Okay, great. So then from here, we want to, now that we have pi prime, we need to define what the bounce path, the bounce pi of this is, right? So this is something that we've seen before, but the point is that we want bounce to equal, so goal 2 is that we want the bounce path. So we want bounce of pi prime to equal area of pi. All right, so how do we do that? So the bounce path, we've seen this before, right? It's precisely if we look at, copy, paste. If we were to look at this path, then the bounce path would be the one you get by just going up to the north, bouncing back all the way up and down, right? That would be our bounce path. So this is, as always, the bounce path that we saw before, right? And for this bounce path, we can define bounce blocks, which are just going to be these spaces, right? So here, we're going to denote this. This is 3 spots. So this is 0, 0, 0. This is 1, 1, because we have 2 blocks. So that the bounce sequence, B of pi, is going to be 0, 0, 0, 1, 1. Right? So this is what we're going to call the bounce sequence. which splits the diagonal, right? And obviously then we're going to say that bounds of pi prime in this case is going to just be the sum of the bi's from I equals 1 to n. Okay. Ooh, sorry, my iPad just froze. I don't know what's going on. What? Okay. Sorry, let me just restart Notability. I don't know what's going on with this. Okay, there it is. Okay, and so then what we see is that then B of sigma I is just AI, which allows us to say, all right, bounds of pi prime is equal to the area of pi, right? And so that's not too bad. So now we've translated bounds, we've translated, oh, we haven't translated dim to inv, we'll get that. So then next goal is to, so this is goal 3, is to, we have touch, we want to define touch prime for pi prime. So touch is also going to be a little bit different. So how do we define our new statistic touch prime from touch, right? So the first thing we want to do is we're going to set L to be the number of north steps from 0, 0 before we touch on each step, before touching, I don't know how to spell, goodness, touching an east step. So it's basically how many steps do you go north before you turn east? And then the second thing we're going to do is we're going to set pi prime or pi tilde to be the remaining path. Right, so that pi tilde is going to be, or sorry, pi prime, right? Pi prime is going to be, you apply L north steps, then you go east, and then you have pi tilde, which is the leftover. So let's do an example. Suppose our path was, we went north 3 times, then we went 1 east, and then we had something else like this. Then in this case, right, L is going to equal 3, right, because we went 3 north steps. Then we went an east step, and then pi tilde is going to be this leftover. So this part right here. This is going to be pi tilde. So we're just cutting it up. And then once we have this pi tilde, we're going to set Ti to be the bounds of the following path. So we're going to set n I plus 1. We're going to east steps n L minus I east of pi tilde. So this looks a little weird. We'll do an example and it will be a lot less arbitrary because right now I'm just giving you some weird definition. Oh my God, Notability, why are you freezing? Sorry, I'm like, it's so annoying. Just kill everything. Okay, sorry. Okay, so Ti is going to be this. And then step 4 is we're going to define our new statistic called touch prime of pi prime to be the following sequence. So it's T0 minus T1, T1 minus T2, etc. TL minus 1 minus TL. So let's do an example because it's much easier to understand all of this with examples. So suppose our path is the one I just wrote right above, right, with that same pi tilde. So let me do this in red example. So let's start with I equal to 0. What is that going to look like? So I is going to 0. We're going to look at the path n e n3, right? Because I is 0. I'm just plugging it into this formula right here. Of and then east again of pi tilde. So we draw pi tilde, which is let's say 2 steps east, 1 step south, 2 east, 1 south. And then what is our picture going to look like? Well, we're just going to do 1 east, 3 south, 1 east, and 1. Sorry, I'm reading it backwards, which is why I'm saying south instead of north. So this is what I equals 0. And you'll notice that this dict path is longer than the previous one. So we're adding 2 extra steps in this and in these new dict paths. Okay, so we have this path, and now we just have to compute the bounce sequence from this, right? So let me draw the diagonal in, I don't know, black or something, right? And if you just go through and draw the bounce sequence, which is this one, right? This is 0. This gives you 1, 1, 1, 2, 2, right? Then b of pi here is just going to be 0, 1, 1, 1, 2, 2. And then you basically iterate this for all of them. So I equals 1 is going to be the same thing, except now you have a different dict path, right? So now you have, let me see, n squared, n squared, east, and pi tilde, and so on, right? So what is this? So let me just redo it again. So we have 2, 1, 2, 1, and then we do this kind of a path. So we do an east, we went north twice, we did an east, and then we went north twice. And you'll notice that at each step, all we're doing is basically kind of taking this square and moving it outwards or moving it inwards. And that's what the eyes are corresponding to. So let me just. Right, because what did I do here? All I did is I took this corner and I moved it in. That's how I got from here to here, right? I took that corner and I undid it. So I reduced the area by 1, essentially, is what's happening. And when I equals 2, right, it's going to be the same thing, except you're going to move both of these down, you know, and so that's what you're doing. You're basically pushing the squares in one at a time. Okay, so if you then do this, you do the same kind of a game. You look at the bounce path, right? And then you look, all right, well, this is going to be 0, 0, 1, 1, 1, 2. So then b of pi here is going to be 0, 0, 1, 1, 1, 2, etc. and so on. So I'm just going to tell you what it is. So for I equals 2, you get b of pi equal to 0, 0, 0, 1, 1, 2. And then for I equals 3, and I encourage you to just do this on your own. It's not very hard, but it adds a lot of understanding, or it helps you understand. Wow, English is hard. And then I equals 3, you're going to get b of pi is going to equal 0, 0, 0, 0, 1, 1. Okay, and what that tells you then at the end is that touch prime of pi prime is going to be, so actually, let me.
Nicole, quick question. Yeah. Are we doing the bounce path from the bottom now instead of the top?
Yes.
Ah, okay. That works.
Yes. Yes.
Sorry. Thank you.
No, absolutely. So what this means here is then here T0 is just the sum of these things. So T0 is going to be 7 because it's the bounce of this. It's the sum of these numbers. T1 is going to be 5. T2 is going to be 4. T3 is going to be 2. So yeah, and then the touch here is then just going to be, all right, so you get 7 minus 5 is 2. We get 5 minus 4 is 1. And then the last entry is 4 minus 2, which is 2, which if you look and compare to what we had before with touch pi, which I did compute somewhere. Where did it go? Where did I define?
Was that 2, 1, 2 example when we were like, oh, that's
yeah,
symmetry?
That's exactly here. So when we talked about the touch composition, right? And that was exactly it. This was 2, 1, 2 reading from the bottom to the top, right? You get this composition. That's exactly the same. So this was touch pi, right?
Mm-hmm.
And then we constructed the pi prime of that example. We computed the new touch prime, and you see that it's exactly the same thing, right? So the whole point is that this is in fact equal to touch pi. So all we're doing here is we're just saying, look, we computed we had pi, we want to define these new dict paths, so we need to translate all the old statistics to this new dict path under this map, which is basically just conjugation by this permutation sigma, right? But we need to translate all the information over. Okay, so now we have touch pi equals touch pi prime. I leave that as an exercise to prove why that's true in general. So exercise is prove touch prime of pi prime is in fact equal to touch of pi. It's a cute combinatorial exercise. And then now what we want to do is we want to translate, so the next goal, well, orange. The next goal 4, my God, there's so much material to cover, is to transfer the statistics over. So transfer the statistics to pi prime w prime. And what do I mean by that? We need to know what inversions are. So we're going to define this new statistic called inv of pi prime w prime. And what is it going to be? So it's going to be the set of cells ij in area of pi prime such that wi prime is bigger than wj prime, right? Which is really just sigma applied to dinv by w. And we have little inv of pi prime w prime is going to be the cardinality of the set. So this is always, of course, the same. And then here our word w prime, the sigma ith position is just going to be wi, which is essentially just telling you that w prime is sigma applied to wi, right? So you're just permuting the word. Okay, so I want to do an example, but we're a little short on time and I really do want to move along. And this is just, as always, following the definition. There's nothing too exciting happening here. So let me just move on to the next definition that we need. We're going to define the corners of pi prime. So the corners of pi prime are going to be the pair sigma j plus 1, such that our co-area sequence is the same on those points. So these are known as the corners, right? So let's see if I have a nice example. It doesn't matter. I mean, the corners are pretty self-explanatory in the sense that if you have a dict path, let's say whatever, something like this, then the corners, and imagine it's square, the corners are just going to be these boxes. They're the boxes of exactly what you would think a corner is.
Don't you mean then that x is not equal? That xj is right? I mean, where xj is equal to xj plus 1 is wherever you have a vertical run, right?
Yeah, but so this is, these are corresponding to pi. So this is the
Oh, but that's
co-area.
proxy of pi
So
prime.
this is like the co-area for pi, right? So it's weird using statistics for the previous path, not the path, not pi prime.
Yeah.
So it's there's this weird translation where it's not, even though it corresponds to, so if this is pi prime, this is what it corresponds to, like those squares correspond to these corners, but it's not obvious from the definition that that's what it means unless you think about it. But essentially, like, this is the formal definition, but what it actually is doing is just picking out those corners. So if you have the picture, you know exactly what it is. Yeah, so these are the corners of pi prime, but this are co-area for pi, and this is not pi prime, right? So you're using a different sequence. I emphasize that. Okay, cool. So then that leads us to our next definition. Sorry, today's a little definition heavy, which is we need a new definition for a word parking function is because we translated everything. So a word parking function for pi prime are set of words, zn, bigger than 0, right? So same kind of a thing. But before our word parking functions, we just had the condition that they had to be decreasing down the columns, right? Here, our condition is going to be seemingly different, but it's actually the same. So why? If we have wi prime is bigger than wj prime, right? For I and j in c of pi prime. So here, the condition is that the words, the corresponding words, the entries of the word corresponding to the corners satisfy this condition, which seems really, really, really weird. But essentially what ends up happening is that if you look at the word and you look at the inequalities that said like, okay, you're in this column, so this, run in the word has to be strictly decreasing, the permutation takes those entries in the word to precisely the entries that the corners are measuring or labeling. So this is, let me just do an example, because I think this is kind of it doesn't seem obvious until you see it. So let me actually do a bigger example, because I think it's easier seen that way. Yeah. So let's suppose that pi is this. So we do 1, and then we do 3, 1, we did 2, 5, 1, 2, 3, 4, 5. Then we did 2, then we did 2. So suppose this is my dig path. We'll just draw the diagonal here. And let me label it.
And not your pi or your pi prime? So
let me call this pi. This is pi. So this is 9, 5, 2, 1, 2, 5, and 3, 2, 3. So let's suppose this is my pi. And so here, W is going to be, 9, 5, 2, 1, 5, 2, 3, 2. W prime, so, maybe I should probably tell you what sigma is. So I'm not going to run through the full example, but here, sigma is the permutation. Do I have it written out? I definitely do. I just need to find it. So here, sigma is going to be the permutation 1, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8. It's going to be 1, 2, 4, 6, 7, 8, 3, 5. So if you want to know how I got this permutation, just do everything we've done for pi prime. It's a good exercise. And then check that you're getting this. So if we do this, then here W prime, it's just a matter of following this permutation, right? And rewriting the word. So we would get 9, 5, 3, 2, 2, 1, 5, 2, right? And what did I do? Well, 1 and 2 are fixed. Then 3 is supposed to go to 4, so 3 went to 4. 4 went to 6, so 4 went to 6, and so on. And I just did this for the entire word. So W prime is really just sigma applied to W, right? And then from here, what we want to check then is that W prime really is it's a word parking function in this new framework, right? So we knew that this was in WP. So the question is this in WP prime of pi prime. So it needs to satisfy this condition. So in order to do that, let me just tell you what pi prime is, because we need to know what the corners of pi prime are. So pi prime.
Nicole, just
yes.
to verify for this, are we okay with having a 9 in our dig path, the label dig path?
Yeah.
Because if there's only 8 rows, maybe I'm remembering the definition wrong, but I thought the limit for the numbers was n.
So word parking functions, right? You can let the numbers be whatever you want, because you're not limiting the number of coefficients, right? You're not saying like you can't have you can only have variables 1 through x to the 8. You can have variables 1 through x to the 100 if you'd like.
All right, so there's an infinite number for each one.
Yeah, it doesn't matter. So the entries, the only condition on word parking functions is that the entries are decreasing in each row.
I mean, it's kind of like when you think about like Schur functions in Tableau. If you want a
Mhm.
symmetric function, you don't limit the values. You just have inequalities.
Okay.
in there.
Exactly. So the only condition here is that you're decreasing each row, but the numbers can be whatever, as arbitrarily big as you'd like. Yeah. Okay. So then let me just tell you what pi prime is then. So for this example, and I really, really do encourage you, do it on your own. The example I was working with before is a little too small to really get a good handle of this, which is why I'm suddenly changing to a bigger example, but it was good enough for the smaller stuff. So 1, 2, and then 3, and then 1 and 1. No, don't curve it. Okay, so this is pi prime associated to that pi. It is not, I'm not saying it's obvious. I'm just saying, believe me, it is. That's what it is. Do compute it. If you get this pi prime, or sorry, once you get this pi prime, then you can actually see that the corners here are going to correspond to, this is a corner, this is a corner, this is a corner, and this is a corner. So you have 4 corners. So the corners of pi prime are going to,
Even without drawing pi prime, we could have gotten the corners from what you wrote before, because you have sigma written there.
oh yeah, you're
You
right.
can see the x's are 2, 3, 4. And then
Yeah,
six.
you're completely correct. From the definition, you actually don't need it. I guess I don't like that definition, and I like the picture version. But yes, you're completely correct. You don't actually need to do it. You can just, from this definition, you can just get it exactly.
Then
So here, you're gonna get 2, 4, right? You're gonna get 4, 6. You're gonna get 7, 8, and you're gonna get 3, 5.
2, 6. Oh no, sorry.
Did I? Yeah. Okay. And so if we go back to this, what is the condition that W is a word parking function? Like, what does it actually mean? So it means that we're going to look at the blocks, and it means that 1 is bigger than, sorry, 1 is smaller than 2, smaller than 5. So 5 has to be bigger than 2. 2 has to be bigger than 1, right? 2 has to be bigger than 5. Or sorry, 5 has to be bigger than 2. Right? I'm just looking at this block. That's these two. And then you get an inequality here. So these are the inequalities that are going to determine that this word is a word parking function. So how does that look when we translate it over here? Well, that's exactly saying that if we look at positions 2 and 4, so what are positions 2 and 4? So this is position 2, and this is position 4, right? So position 2 and 4, that this condition has to hold, right? But that's exactly saying that 2, 5 has to be bigger than 2. That's these two. Right? So it's really just tracing where the inequality is going to end up in the new word and imposing that as a condition. And somehow the points where these inequalities hold are precisely captured by the location of the corners. So that's why the corner statistic or sequence or whatever set matters here. Right? We do the exact same thing with 4, 6. So 4, 6 is precisely encoding yeah, that 2 is bigger than 1. So that's this. Yeah, does that make, sorry, yeah. 2 prime and 4 prime. And then, oh yeah, of course. So then 4 and 6 is, maybe let me do this in a different color. So this is 4 and this is 6. But that 2 came from here and that 1 came from here. So the fact that 2 is bigger than 1, which is 4, 6, right? This is coordinate 4, 6, is the fact that 2 has to be bigger than 1. Does what I'm trying to explain make sense? Like how you're really just tracing that inequality, and under the permutation, the two things that were adjacent get split up, and that split gets that, like where they get mapped, that pair gets encoded as a point on a corner. So saying that the points corresponding to the index by those corners have to satisfy that inequality is exactly the same as just tracing what that original adjacent inequality was under the permutation. Right, so what other inequalities? 7 and 8. So if we look at 7, that's this one, and 8 is this one. So 5 bigger than 2. Where did that 5 come from? That 5 came from, let me see, where did that 5 come from? That 5 came from here, and that 2 came from here. So it's comparing piece point-wise exactly what you want, right? And then 3 and 5 is exactly encoding this one and this one, right? Which is right here. So this becomes this and this. Does that make sense? Okay, wow, I'm super overtime. So let me just conclude it and move on to and tell you what I'm going to do next time. I'm so running late. I'm so sorry. So in conclusion, what we get is that basically WP prime of omega prime is really just sigma of word parking function. So it's sigma applied to this. And if you take the sum over touch pi equal to alpha of t to the area, which was the right-hand side of the shuffle conjecture, or sorry, the compositional shuffle conjecture that we were interested in, div pi x of w, right? W in word parking functions. This is really the same as, well, great, as t to the bounce, because this is bounce pi prime, right? Where we're summing touch becomes touch prime of pi prime equal to alpha. And then here, our w becomes w prime in word prime of parking functions, right? So all the conditions get translated over. And here, dinv becomes inv of pi w of xw. So there's a perfect translation of all the statistics and everything we wanted to this new framework. And what the goal, so we're going to denote this by, we're going to call that d alpha of qt. Right, we're going to just to give it a name because it's easier than to continue writing it over and over again. And the objective is to study essentially this d alpha qt as a function of pi. Right. So maybe let me stop because I'm already over by like 10 minutes. And then let me tell you and basically tell you that next time what we're going to introduce are these things called characteristic functions, which is just a generalization of this piece. So that's what we're going to focus on is that internal sum. We're going to generalize that. So we're not just summing over word parking functions. We're going to prove some properties about that and then introduce a completely new algebra and show that these generalized internal sums, which are secretly, by the way, these are secretly just these f pi's that we saw before, that those sums can arise as, or can be generated by these new objects in these new algebra. So that's for next time. So let me just stop here before I keep on talking. Thank you for sticking around.
Let us thank our speaker.
So I don't have any exercises because the exercise that I had is based on stuff that we didn't get to. Yeah, I can either continue talking or we can just discuss it if you guys have any questions. I don't know. Tell me, what do you guys want to do? Or questions?
I had a potential suggestion.
Yes.
But I feel like I should let students speak up first, though.
I'm still processing all the information. So if you have a suggestion, like that's probably okay. There was a lot of definitions. So I think a lot of these are just going through examples probably. So maybe if there's like some bigger example, we can go through this whole algorithm again. I don't know.
Yeah, so I can actually, if you want, we can do this pi that I did at the end, this much bigger example. We can just redo all the steps, all the statistics in like gory detail. That's easy. And I think it's helpful.
Yeah, I think this is a good idea, and maybe I could do it because I don't know how to do it, so
100%. Yeah.
we'd have some more time.
Monica, did you have a suggestion just in case?
Well, my only suggestion, and we can do it in the context of this example or after we go through a bigger example as an alternate way, but like going between pi to pi prime.
Mm-hmm.
And this is sort of good if you're going to read Mellit's other papers. One way to do it is you break symmetry slightly, you perturb the diagonals a little bit,
Mhm.
and then that actually totally orders all of those corners, the coordinates on them. And then another way to show going from pi to pi prime is actually, as you read your north and your east in a given order, if you resort them numerically in that slightly perturbed order, and then you build that path of those new sequence of northeast, that's another way of getting pi from pi prime that I find visually, I like it a lot, instead of going from area to area prime.
Is it, wait, so it gets pi from pi prime. It doesn't give you pi prime from pi. So it's like the reverse map? Is that what you're saying?
No, I think, well, again, I'd have to check. I mean, I'd have to check on the example, like which one it actually is. I just know it's going from in one direction to the other, and I'm not sure which one lines up with yours, which is why it's maybe not a very good suggestion until the details are worked out.
Okay. Okay. Well, we can, this is in his rational paper, right? Is that?
Yeah.
Yeah,
So
yeah,
it's the slight perturbing so that you just get a complete order on all of your steps. And breaking ties where things touch the diagonal is a nice trick to learn, and so it might as well introduce it. It didn't exist maybe in the older stuff, but I think going forward, it's good to cast it in that more modern way of thinking.
Cool. And then just as a question, you said that this sweep map is what you called it, that somebody else, that it's due to somebody else. Who? Just
I think like Armstrong and Lohr and possibly Rhodes.
Okay.
I don't have all the correct.
No, I was just curious.
Either sweep or zeta. I get confused. If Eugene was here, he would know the difference.
Okay, awesome. Well, in that case, let's migrate to doing a thorough example. Foster, you are, I think, co-host now.
Okay. So I'll take over the screen sharing. Okay, and I've got this nice little grid. So maybe I can draw pi, and maybe I'll do it with the scale where, 2 boxes here is a box. So we got northeast, and then 3 norths, east, and then 2 norths. And then what was it, 5 easts. Okay, so this is our pi. And we even had a word parking function here, so we put some numbers in them. Okay, and then also just for the sake of it, I'll draw in this diagonal. Oh, okay, wait a minute. It's not lining up. 3, 1, 2. Well, maybe there should only be 40 steps.
It should be 5. Did I do it wrong? Maybe it's 4. Let me check in the one mine. No, it's not the one I drew. It's only 4. Sorry, not 5. Definitely 4.
Okay, there we go. So that's our pi. Okay, so yeah, what kind of things can we do? So let's see, I guess area. I can write the area sequence. So I think that's not so bad. 2, 3, 0, 1. So area of pi equals 9. Let's see. I guess there's touch of pi. That's an easy one. That's sort of just
another question about this one. So the columns are supposed to be decreasing, right?
Oh, like increasing from bottom. Oh.
Right? If they're strictly because the first example we had 4 on top of 3, but here we have them the opposite. So shouldn't it be 9, 1, 2, 5, 2, 5, 2, 3?
4 on top of 3. Oh, it's because I did it backwards in the example. It's the column should be increasing, 100% sure.
Okay.
Yeah, I did it
So
backwards in my
it's not the, okay, that works.
This
So
is
I should
when I
change
come up
these
with
or
my own
not?
examples. So the example I did in the notes, just like invert all the numbers, totally backwards. I'm so sorry.
No,
Okay.
it's okay. So then the definition should be increasing in each column rather than decreasing.
I guess decreasing in each column. No.
But yeah, here,
each
so here
column.
you have, so in the original definition, when we had words, you had decreasing in each column, you had WJ greater than WJ. I guess, yeah, you have WJ plus 1. So I guess you're decreasing going down. Yeah, okay.
Yeah, that is really confusing. I think that's why I got confused. I didn't even notice. Sorry. Thank you for noticing that.
No, it's okay.
Okay, so do the example. Sorry, can we let's do the example where you're increasing, going down each column. So what you had written before. And then let's just fix the definition so that it makes sense, because I think decreasing doesn't make sense if I don't tell you where you're reading it from.
Okay, so you want me to go back to
So what? Yeah.
Okay, bigger numbers on the bottom.
Yes. Because I know this is consistent with what they did. So I just want to make sure we're doing whatever they did in the paper so we don't end up with weird discrepancies. And then I'll just fix the definition so it matches this.
Okay, so then let's see, touches, we're going to look at these.
Mhm.
Is it 152 or 251?
So
Or- yeah.
touch here should be 152. So you read from the bottom going up.
Okay. Sounds good. And then let's see, I guess we could also think about div.
Mhm.
Maybe I'll put this one in red. So let's see, div with a capital G. So I guess so I'll put the ones with the same area here on the bottom. So 1, 2, 1, 7, 2, 7.
Mhm.
Those all have zeros, and then there's, I guess, 3, 8, and 4, 5.
Mhm.
And then I think with the other one, I think the idea is that I've got an I plus 1 and then like an I.
Yeah.
Is that right?
Yeah.
Yeah. Okay. And then I'm supposed to put the bigger number first. So with the secondary kind of inversions we've got, let's see, so 7, 3, does that sound good for this one?
Mhm.
Okay. And then let's see. So 8, 4, 8, 5. Guess that's that. So then little div is 8.
Yep.
Oh yeah, I guess you write div pi w.
No. So that is div. There's
Oh,
div
right.
of pi and then there's div of pi w, right? Because big
Okay.
div of pi is something else.
Okay.
That's 8. Yeah.
Um,
And so now we need to compute div of pi w and little div of pi w.
let's see, how about this sort of pink one? Okay. So let's see, I think my understanding is that for this one, I need to have either a bigger number like this, or I need to have, what is it, a bigger number sort of 1 up.
So it would help me, like I think of it as writing out the W, like the 9, 5, 2, 1, 5, 2, 3, 2, and then putting on top of it the 1, 2, 3, 4, 5, 6, 7. And then I just look at those pairs in
Yeah.
div. And then,
I do the same thing.
Okay, absolutely. So I read the
and then
numbers
I
from
can
bottom
compare
to
them to
top.
the visual.
Is that right?
So 9, 5, 2, 1, exactly like that.
And then
And
you
then
want
can
me
you
to,
stick atop them the 1, 2, 3, 4, 5, 6, 7, 8?
okay, so 1, 2, 3, like that.
Great.
And do I also need to write down the area vector here? Or
I mean, we don't need it right now. So, and then for the div, do you remember? Yeah, it's, you just look at like 1, 2, like the cells in div of pi and check whether, the smaller one is bigger than the second.
Shouldn't it be 953?
953. No, you're not. You don't read the word diagonally. You read the word going up each column.
Oh, I'm thinking something else. Okay, never mind. Yeah.
Mhm.
Okay.
You're thinking of this like permutation that we're going to apply in a little bit.
Yeah. My brain jumped ahead. Sorry.
Okay, so I guess
So I don't
we
think
have-
we keep 2, 7, right? Because so for 1, 2, we've got 9 is bigger than 5.
Mhm.
And for 1, 7, we've got 9 is bigger than 3.
and then
Oh,
5
and then
is
2,
bigger than 3.
7, 5 is bigger than 3. Okay.
So
Yeah,
that's
7,
2,
fine.
7.
Yeah.
But I don't think we have the other ones.
What about 8, 4?
Oh, I meant on the first row.
Oh,
Yeah.
I-
Yeah,
3, 2 is
absolutely.
equal to 2. Okay. And 4, 5, 1 is less than 5. Okay.
So then the next ones, I guess we're looking again for something like this.
Mhm.
Do we have 8, 5?
you should, right?
Yeah. So we've got 8, 5, but that's all of them, maybe.
Shouldn't we have 7, 3 since 3 is greater than 2?
And we do have 7, 3. Yeah.
Hmm. Oh.
Yeah, it's bigger
Wait, so do I want this number to be bigger than this one?
So in like 7, 3, you want 7 corresponds to number 3, and then position 3 corresponds to 2, and 3 is bigger than 2. Therefore, 7, 3 is in the set.
Yeah,
Oh.
so I think it should be 7, 3, 8, 4, and not 8, 5.
Okay. Yeah, so maybe I have the second thing backwards then. Okay, so 7, 3, 8, 4, not 8, 5.
Yeah, and that's 5.
Does everyone agree?
If we're remembering the conventions right, then yes.
Let's see, maybe I can move these things so we still have them. Well, something like that.
Oh, well, you don't want to cut div off. Yeah, it's okay.
Let's see, I can maybe move this over. Can I fit it all in now?
You could shrink it down just slightly.
That's
Oh,
good. Yeah, right there.
right here?
That works.
Okay, sure. Sounds good. So let's see, are we able to do pi prime now? Is there anything else we need?
Maybe the co-area sequence. I find that one useful to just have written out.
Okay. I guess area is green, I'll make the co-area. Maybe I'll just write that up here.
Yeah,
Can
so it's like x of pi.
Can everyone see this? Is that a good color?
It's fine.
Yeah, it's legible enough.
Okay, so x coordinates of cells that are right of the north steps.
So it's just right where you put the reading word, essentially. That's where what you read.
Okay, so 0, 1, 1, 1, 2, 2. Or no, we increase it by 1.
6.
That was fine.
Oh, okay, so I start from 0.
Yeah.
6, 6. Okay. And then I guess.
Oh no, wait, sorry, totally wrong. No, you're right. Because we're starting from like the top right corner. You're right. I'm so sorry. Yeah, it was
Okay.
1, 1 or
Okay.
1, 2, whatever. Yeah.
1, 2, 2, 2. 7. Okay.
And then I guess we want sigma as well, maybe.
Mhm.
So let's see, for sigma, I'm gonna read the entries going like that, right?
Mhm.
And then and then it's the y coordinates. Um,
Yeah.
I feel like maybe it's the inverse permutation of what I was imagining. Let's see, so okay, sorry, I know everything's getting a little cramped. Let's see, so the first thing I read is in y coordinate 1. The second thing I read is in y coordinate 2. The third thing I read is in y coordinate 7. So do I put a 3 here or do I put a 7 there?
You put a 3 in position 7. So 3 under 7. Yeah.
Okay. So then let's see, 4, 5, 6, 7, 8. Is that okay?
It agrees with what I have written, which I think is hopefully correct.
That's a good sign. Okay, so pi prime is the unique dict path such that the area is this thing, and I've written sigma of din of pi. Okay, so let's see. So now pi prime is such that so I just take these, I take these ones and I apply sigma.
Mm-hmm.
So 1, 2 goes to 1, 3. Is that?
Huh? But sigma starts 1, 2.
But one goes to 1.
Sorry.
Yeah. Oh yeah, and
Sorry.
2 goes to 2. Yeah.
Okay, 1, 7 goes to 1, 3. I think I was doing the next one. Is that right?
Yep.
Okay, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 5, 7.
Checks out.
Okay, that's good. So maybe I'll just draw something that's 1, 2, 3, 5, 6, 7, 8, and then okay. So I guess I want to include this one and this one. 3, 4, 4, 5, 5, 6, 5, 7, 6, 7. So maybe I want it to go like that.
Yeah. I agree. Does everyone else agree?
Not quite there yet. Give me a second. You guys think a lot faster than I do.
I already did it. You don't know how slow I was when I computed it. Let's keep it.
I'm getting some help. I'm getting some help. I'm confident that I can just write down whatever and you'll tell me. Do you have like, do you have a really good feeling inside of why, it's a bijection and, how area and div and bounce are connected?
Me? No. No. I mean, this is all maybe Monica, maybe she's thought about this a bit more, but I don't. To me, it's just like there's this magical formula and these magical definitions that seem to give you bijections, but there's zero intuition behind them for me.
So, I think the way I usually go from pi to pi prime, which is this other way, which might be pi prime to pi, going between area and din, I'm good. But bounce has always been a little, I've never really looked at bounce, so.
Back when I was doing that thing with the zeta map, we had this idea that we would sort of take the area vector and we would kind of build it up by putting the zeros and then the ones and then the twos
Mhm.
inside. Do you think it's something similar to that or just not?
I don't know, because I don't think about the map that way. So I'd have to redo some examples and see.
Okay. Let's see, so we've got pi prime. What do we want to do? Do we want to do touch pi of pi prime? It's also 12:30, so if we want to stop, that's also okay.
Either touch, can we do like the WP prime of pi prime yet? Or do we still need more?
I'm almost done. There's just one I'm confused about. Because I think the path, I mean, yeah, like I got a different path.
So if the red, if you label the red squares, those
Yeah.
red squares, they should just look exactly like the area prime squares.
Well, yeah, so I have different red things, that's why. Oh, or maybe I just don't have, oh, it could be that I actually, no, I do have the same, I just don't have that. Okay, I see what I did. Okay, no, that's okay, it works.
I would say we should compute inv and not touch prime, because touch prime takes a lot of iterations of applying this kind of recursive definition of flipping the corners.
Okay, so would someone help me out with this, please?
Yeah. So do you want can I give you the definition?
Oh,
Or
yeah.
do you want the actual?
Oh, maybe you could remind me what the definition is.
Right. So it's the cells in area pi prime, where Wi prime is greater than Wj prime.
Wi
Prime.
pi prime is bigger than Wj prime.
So
So
maybe
we should write W prime first, I guess.
exactly.
Okay. Well, W prime. I haven't put numbers in the cells. Is that a problem? Or what's W prime?
It's just sigma applied to W.
Oh, okay. Okay. So W prime applied to, yeah. So let's see, W
You
prime.
can write W prime right underneath W. So it's going to start out 9.5.
Okay, so the third thing becomes the fourth thing, is that right?
That's exactly it. Yep.
Okay.
1, 2.
Oh, yeah, I might be doing
I think
sigma
we find
inverse.
sigma inverse.
Yeah, okay, so.
So
Two goes
if you
to
drop a
the
little
four.
braid picture right under W, like there's two straight lines coming down from 9 and 5.
Yeah, I do the braid thing too. Otherwise, I can't read
So,
this.
so yeah, so just go up to where we can see W in blue.
Oh, or maybe I'll just write it again. 9, 5, 2, 1, 5, 2, 3, 2. And then I should write these. And then you want me to write sort of 1, 2, and then.
Not necessarily, but
Or
okay.
just like draw a little braid diagram, kind of like 9
Like
goes
draw
to
a little
9.
straight line coming under the 9 and coming under the 5.
Okay, okay, I think that sounds good. So this. And
Right.
then,
Exactly.
Yeah.
7, 3, 8, 5, something like that.
Perfect.
Okay, yeah. I did have a feeling like there was a chance I would be writing sigma inverse. So 3, 2, 2, 1, 5, 2, something like that.
Good.
Okay, cool. Let's see. So inv pi prime. Okay, so I just need to check where they're. Right.
Number 2.
So 1, 2, 1, 3, 2, 3. Those are all good.
3.
And not 4, 5, and not 6, 7. And then do I have 5, 6? And 5? Do I just have 5, 6?
You're missing one? No? Am I crazy? Maybe not.
I might be doing
You're missing
these ones
3, 4.
backwards
You're
again.
shifted over a little bit, right? So 3, 4. This is bigger than 2.
Oh, okay. So 3, 4, and 5, 6.
Yeah, that's what I have too.
Oh, also, sorry, I just realized the end that was end of pi w pi prime comma w.
Mm.
Yeah. Yeah.
Okay, so we've got 5 of these. And then, oh, is that supposed to be the same as this?
It's exactly supposed to be the same as that. Yeah, that's the whole point. That's the translation that you're getting.
Okay, and then these match up with that. And well, I guess next week we can think about touch prime some more and some things like that.
Yeah. Yeah, touch prime, like I said, is kind of annoying to compute just because you do have to do all these like, and I think for this one, there's 27 different paths that you need to draw, which is, it's awful. Yeah. So this is like, for this example, it's really big, which is kind of why I chose the smaller example, even though it wasn't as interesting. So you should definitely do it on your own, but I do not recommend doing touch prime here.
Or I thought we have like one path for each different value of I between 0 and L.
Oh, maybe you're right. Maybe it is only 3. Oh, you're right. Never mind. Maybe you have 27 different terms. Maybe that's why I was like, maybe that's it. Maybe you're right. You do only get 3. Okay, ignore me.
Oh, no worries. Well, yeah, it's past 12:30. Thank you to everyone who stayed and helped me out here.
Thank you. Thank you, Foster.
Look forward to see you next week.
Bye, everyone.
Okay, and don't forget to stop the recording.
Yes.